It is time to move into our second lecture on this thermodynamics unit, our last unit here. This one has topics 9.3, 9.4, and then skips to 9.6, which is a real short thing right there. But we are going to start to piece this whole thermodynamics thing together today. This is a really important concept here, and they'll use these initials TFP to represent a thermodynamically favored process. What that means is it proceeds without any assistance from the outside system. A lot of times the word spontaneous is used. Thermodynamically favored process is a better and more updated term for that. Water will evaporate if you leave it sitting out. That's just spontaneous, right? It just happens. It's a TFP. Iron will rust. It just happens. Sorry for those of you that have those really old cars, but that's what is going to happen. If you put salt in water, it's going to dissolve. You don't even have to stir it. It'll take a little longer to dissolve, but it's just something that the forces of nature allow it to happen. Now, there are also processes that are unfavored. For instance, if you have water at 75 degrees Celsius, it's not going to boil, no matter what. And water will not freeze at 15 degrees Celsius. This chemical reaction here, the reverse, you could take iron oxide, combine it with solid copper, and go back to iron. That is certainly not something that just happens. You can't just throw a little carbon on your rust and have it turn back into iron. So these are pretty intuitive things. I think a good example of the fact that these processes are reversible and opposite would be if you were at 10 below Celsius. That's plenty cold to freeze water. So this becomes a thermodynamically favored process, a TFP. If you go from solid to liquid, that's melting. It's not going to melt at minus 10 degrees Celsius. It's just going to stay ice, so that is a non-TFP. This is important. We're going to relate this to enthalpy now. Exothermic reactions are often thermodynamically favored. So what I want you to do is circle this word right here. They're not always, but they are often. All right. And then this is a pretty good statement to highlight right here. Nature tends to favor processes that cause a reduction in energy. There's another one you can use with your parents. Hey, nature tends to favor low energy, man. I know I sure feel like that at the end of the week here. So exothermic reaction, the bonds of the products contain less energy, and that's usually favored in nature. Okay? Now, this one, endothermic reactions can be thermodynamically favored. They can be. So you can see these all have delta H's that are positive. And these processes, if we look at this, liquid water going to gas has a positive delta H value. That's an endothermic reaction. And when it does that, it lowers the amount of heat in the system. All right, so it's endothermic, and it makes it colder. You can think of sweat evaporating, and it will cool you off a little bit because the average kinetic energy is going down because the molecules with the highest energy take off. That's why you have a little bead of sweat. They're going to break free the highest energy ones, lowering the average kinetic energy, which lowers the heat and the temperature of the system. Okay? Same thing if you had some propane gas evaporating, that also would be a cooling process. And the dissolving of salt is slightly endothermic. But these are all thermodynamically favored. They're all TFPs that are endothermic. It's just not as common. Now, nature tends to favor the low energy systems, but in these cases, clearly these things do happen. All right. So, exothermic reactions are favorable when delta H is less than 0. All right. So, those are the processes that tend to be favored. And from yesterday's lecture, a greater degree of disorder is favorable. So you know that, second law of thermodynamics. Okay? As a matter of fact, write that right there. That's one of those things we're going to check on your notes. Second law of thermodynamics. Right there. Process, we favor disorder. All right, so we're going to look at this in two different ways. One is we can look at the entropy of the entire universe, which is a pretty hard way to study a small system. And we can do something called the delta G, which is Gibbs free energy. And what Gibbs free energy takes into account is the entropy and the enthalpy. And we'll see that coming up. Okay? So let's talk about this first one. This little oval right here represents the universe, the entire universe. The infinite universe is represented by this oval. On my computer, it's about 8 inches across, the whole universe. If you're doing this on your phone, probably about the size of an egg, a small egg actually. But that has to represent the universe. Now, here's a system that you're studying, and there's the surroundings. So if you think about the system and the surroundings, you can make this statement right here. The change in entropy, so let's write the word entropy in here so you get that hammered into your head when you're reviewing this in late April here. So the change in entropy equals the change in entropy of the system plus the change in entropy of the surroundings. Now, if the change in entropy of the universe is greater than 0, then the reaction is thermodynamically favored. Okay? So you need these systems to prove that if there's an increase in disorder, increase in randomness, that's favored in the universe. All right? Kind of an abstract concept right here. So if you look at an exothermic reaction, heat is leaving the system. Okay? Heat is leaving the system, and then that means the excuse me, the delta S of the surroundings is greater than 0. All right? In an endothermic process, the heat is going into the system, and the delta S or S decreases, meaning that the delta S is less than 0. Okay? So those are just some things to kind of hammer home. So this is a good summary page for all those sort of abstract concepts. So just circle this whole slide and say this is for the universe. It gives you the equation review, reviews this increase in entropy, and exothermic would also tend to favor that. And it must also be thermodynamically favored, all right, for the delta S of the universe to be greater than 0. Okay? So that's the summary. That's a really good summary of this number 1 right there is the previous slide. Now, what is this delta G thing? Gibbs free energy. Number 1, super important, because you can't really say you know thermodynamics until you talk about delta G, because this takes everything into account. And here it is. This slide, you're going to circle the whole slide, and you're also going to put some stars around it too. That's how I know you're watching the videos. So you're going to circle it, and you're going to put some stars, little or asterisks or little stars, whatever you favor. All right, but let's walk through this. This is delta G equals delta H, which you know is the enthalpy. Not really temperature. As a matter of fact, temperature is right over there, but this is the heat we can use loosely. And for those of you in class saw that heat and temperature weren't the same thing when we were melting those ice cubes. The temperature, of course, in Kelvin. Entropy change, I want you to change this right here. It is almost never given in kilojoules. So cross off the K there. This is joules per Kelvin. The reason being, if you remember from delta S, we talked about this, is that these values are usually smaller. You're going to want to convert it into that, but I just want you to note that when you're given these values, this one will always be joules per Kelvin, and you're going to have to change it into kilojoules. So, I mean, that's why that says kg, but I wanted to remind you that that's going to be given in joules. Obviously, if you're going to subtract the two things, you'll have to convert them to the same unit, and that's what we always do, is convert the entropy into that. So, if delta G is less than 0, the process is thermodynamically favored. I always remember it's very similar to when we talk about delta H. When delta H, negative, exothermic, gives off heat. Delta G is favored if it's negative. So you want delta G to be negative. And that makes sense because we said endothermic processes tend to be favored. Well, that's if if you have that negative value in there, then that you got a big negative number here. It's going to make this number negative. Now, it could change when you take and multiply the entropy by the temperature. It is possible that an exothermic process could be non-thermodynamically favored if that number was big enough to counteract the delta H. So that's going to be really important. All right, now, so that means delta G is defined as the maximum amount of energy that can be used to do work. That's kind of a little physicky, but it does help explain this a little bit. This, with temperature times entropy, and remember entropy is always per degree Kelvin, so those kelvins will cancel out. This is the energy to create disorder, and this is the energy to transfer heat. Okay? So that should make a lot of sense here. Now, when we write this equation, just like what we saw with delta H, oftentimes you'll see these little superscripted zeros. That means standard state, 1.0 molar concentrations, and then the gases are at a pressure of 1.0 atmospheres, or 1 bar, roughly. Okay? So that is why they have those little zeros in the equation. Oftentimes you'll see it written like that. Okay? And this is the end of the first video. Please continue so we can finish up this packet.